This video marks the start of topic 4, which is statistics and probability. We will assume that you will already have a knowledge of basic probability and basic statistics, and we're going to take the unit from random variables and probability distributions. Now, in this video, I want to start with the definition of a random variable. I will give you a few examples of that, and then we're going to start discussing probability distributions. In particular, we're going to begin with discrete variables. So a random variable is a variable that takes different values according to chance. The values that that variable can take are the outcomes of an experiment. For example, if the experiment is flipping a coin, you can have two outcomes. It can be heads or it can be tails. If you're tossing a die, the values that that variable can have are 1, 2, 3, 4, 5, or 6 if it is a six-sided die. Of course, we are going to assume that we know all of the values in the sample space for this variable. So we are going to learn what are going to be the probabilities associated to each of those outcomes, and with those we're going to build the probability distributions. Let's consider the random variable x defined as the sum of the outcomes of tossing two-sided dice. We can see here in the table all the possible outcomes that we can have. We can have 1 in the first die and 1 in the second die, 1 in the first one, 2 in the second one, etc. In total, we are going to have 36 total outcomes. However, the sum of the outcomes of tossing the six-sided dice does not have 36 outcomes in itself. This variable x only has a limited number of outcomes because many of the sums that we can build with the two results from the two dice are repeated. So in reality, we are only getting values that go from 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. All the other outcomes are repeated outcomes. They are not new. So our sample space for this variable is going to be the numbers from 2 to 12. Natural numbers from 2 to 12. Say we wanted to build the probability distribution that represents this random variable. We're going to build a table where the first row is going to be assigned to the values of the variable. So in the first row, we want to have the values of x. And the values that we can have are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Now in the second row of our table, we are going to build the probabilities for each of these outcomes. The probability of getting the value x is going to be, now we need to count how many of those outcomes gave us a result 2. There's only one outcome that gives me 2 out of the 36. So this probability is going to be 1 over 36. Now I want to consider all the outcomes that will give me A3. So the probability of getting A3 from the sum of the two dice is 2 out of 36. So we can continue to do this until we fill the whole table all the way to 12. And now by completing the table, we have completed the probability distribution for the random variable x. Now let's talk about some of the properties of this distribution. So of course, when we add up all of the probabilities that we find in this table, the probabilities will add up to 1. This just simply means that whenever we perform the experiment of tossing two dice, we are going to get 100% of the time one of the outcomes from 2 to 12. One more thing we can look at from here is we can start asking questions about different combinations of probability. For example, if I ask you to find the probability of finding an outcome that is less than or equal to 4, all we have to do is consider all of the outcomes that meet this characteristic. So in this case, it would be 2, 3, and 4. And we need to give the total probability based on the sum of these probabilities. So this probability of getting an outcome that is less than or equal to 4 is going to be 1/36 plus 2/36 plus 3/36, and that is equal to 6/36, or 1/6. Now, say you wanted to find the probability that your outcome is more than or equal to 11. In that case, the probabilities that you would be looking at are for 11 and 12. So you will be adding the probabilities 2/36 plus 1/36. That is going to be 3/36 or 1/12. These probabilities are cumulative probabilities. One more example of that would be to find the probability that x is less than 11. In this case, we don't have an equality, so all the results are going to include from 2 to 10 only. We can add all the probabilities from 2 to 10, but you should try to find an easier and quicker way to do this. You already know that the sum of all the probabilities is going to be equal to 1, and you already know that the sum of the last two probabilities for 11 and 12 is equal to 1/12. So if you wanted to find the probability that x is less than 11, the easiest way would be to take the 1 and then take away the 1/12. So this is going to be 10/12 or 5/6. Now let's summarize what we found working with that probability in general. For a discrete random variable x, we are going to find that each of the outcomes correspond to a probability distribution function that we're going to denote as p of x. Each of those individual probability values are going to take a value between 0 and 1. Now the sum of all of those probabilities has to be equal to 1 because there has to be 100% of the time one of the outcomes from the sample space of that variable. Now we can calculate probabilities in a cumulative way by considering the cumulative distribution function or CDF of the discrete random variable x. This corresponds to the probability when x takes values less than or equals to x, and it's going to be the sum of all the probability values up to that value of x. Let's take a look at one example. Radon is a major cause of lung cancer. It is a radioactive gas produced by the natural decay of radium in rocks that contain small amounts of uranium. Studies in areas with high levels of radon revealed that 1/3 of the houses in these areas have dangerous levels of radon. Suppose that two houses are randomly selected and we define the random variable x to be the number of houses with dangerous levels. Find the probability distribution of x by a table, a graph, and a formula. This problem looks like it can be solved with a tree diagram. So let's draw a tree diagram for these situations. So we're going to take a look at the first house. The first house can have dangerous levels or can be safe levels. This is going to be for house 1. And the probabilities for this house are 1/3 and 2/3 respectively. Now we're going to choose a second house. And we're going to call that house 2. And the same, we're going to have dangerous levels or safe levels, dangerous or safe. And we're going to fill in the probabilities. They are the same, it doesn't change house to house. So 1/3 and 2/3. Now we want to see what are the possible outcomes for this random variable x. It is the number of houses with dangerous levels. So looking at the graph, I can have three options, three possible outcomes. And one of them is that none of the houses has dangerous levels. Then the other option is maybe one of the houses. And then the other option is that maybe both houses. And there are no other possible outcomes. It has to be 1, 2, or 0 houses. Now, we can calculate each of these probabilities just by making use of the tree diagram. So for 0, this is going to be 2/3 times 2/3. For 1, we have two possibilities for this scenario. It is 1/3 times 2/3 and 2/3 times 1/3. So we have two different branches in the diagram that has the same outcome, and we just add the probabilities. So 1/3 times 2/3 plus 2/3 times 1/3. And then for two houses, we only have one option, and that is 1/3 times 1/3. I can rewrite the probability for 1. I can rewrite it as 2 times 2/3 times 1/3. And then I notice the other coefficients could be 1 times and 1 times. Now those coefficients that are in purple are binomial coefficients, 1, 2, 1. So I think I can generalize this probability by writing it like this. X equals X is going to be, first I need the binomial coefficient. So N, C, X. And then I need the product of the probabilities. So for the case when X is 0, we need 2/3. So when X is 0, 2/3 has to be to the power of 2, or in this case, if we have in houses, it will be to the power of n, but we'll just use n in this case, so it would be n minus x. And then times 1/3, and this is to the power of x. So initially 1/3 is not in the distribution. When p is equal to 1, we get 1/3 to the power of 1, and when it's x equals to 2, it's 1/3 to the power of 2. So x is going to be the power of 1/3. Now, in this particular case, we have only two houses, so we can substitute the n back, and we get that the distribution for the random variable x can be expressed with the equation 2cx, 2/3, 2 minus x times 1/3 to the power of x, like that. So we use the tree diagram to create an equation for the probability function. Now we can use this information and put it as a table, and that is similar to what we had before. So we know that the possible outcomes for x are going to be 0, 1, and 2. We don't have any other possible outcomes. And the probability for x equals to x, we already found it. It is given in the upper right. So this would be 4/9. This would be 4/9, and then this would be 1/9. Now that would be the table that represents my probability distribution. Now, how about the graph? If we wanted to represent this information as a graph, then what we have to do is a bar graph. So we're going to put in the x-axis the values of the variable. In this case, it should be 0, 1, 2. And we're going to build a bar, like a frequency bar, that goes up to the value of the probability for the value of the variable. So at 0, the probability is 4/9. Now for 1, the probability is also 4/9. And for 2, the probability is 1/9. So that would be the bar graph that represents this probability distribution, the table, and the formula. Now it's your turn. Can you find a graph, a table, and a formula that represents the probability distribution for the random variable x, defined as the number of heads obtained after flipping a fair coin twice? Work on this and show me next time.